Surface integrals is really just an extension to the idea of our line integral. Remember the idea of our line integrals, we're going to integrate some function across the curve S. As we add up all the way across, we're finding the value of this function for every point along that curve. Well, let's do the same thing, but instead of a curve, let's say we wanted to do that for every point on a plane or a surface or any other shape that you get. Well, the idea extends almost exactly the same way. So we're going to integrate for every point on the surface instead of a curve. Remember we were integrating across the curve a second ago. We're going to integrate every point on a surface of some function of x, y, and z. So now we're in 3 dimension, ds. All right, well, how do we actually evaluate something like this? Well, we knew from the past that ds is this. It's 1 plus, I'm going to write this f. It's a different f because I'm going to erase this. F sub x squared plus f sub y squared dA. And that's what it used to be, and it still is, but we got to think about this in terms of something a little bit different. What is our surface? Well, let's say that our surface is some function, let's call it g, of x and y. So in this case, if our surface is some function of x and y, that means that's what z is equal to. So if we think about it in terms of the surface, that means that this is going to be a function of x and y, and we know z is also a function of x and y. So now we can get this in terms of all of x and y. Now when we're going to integrate across the surface, our surface area is still the same. Since our independent variables are x's, we need to find the surface area defined by g, because g is the surface we're integrating across. So this is going to 1 plus g sub x squared plus g sub y squared dA. All right, we're still not integrating across the surface anymore. Now we're integrating across this area, which is going to give us a region, a 2-dimensional region. But what is dA? Well, since our independent variables are x's and y's, this is going to be dx dy or dy dx. Now this formula can change depending on how our surface is defined. Most of the time our surface is z is a function of x and y. But what if our surface was x is some function of y and z? How would that change everything? Well, it would still be the double integral over some region. We'll see what that is. But now we're going to replace x. So this is going to be some function of y and z. And our surface area piece has got to be based on this surface. So that's going to be the square root of 1 plus g sub y squared plus g sub z squared dA. Now what is the region that we're integrating across? Well, dA is the region in the xz plane this time. So dA, or dy dz, so the area is in the yz plane this time when we go to integrate across it. And of course, if it was y was a function of x and z, just change all the letters. So there's our idea. How do we actually evaluate something like this? So let me go ahead and get these out of here because they are just kind of formulas. I'll put it up in just a second. So let's say I said find the surface integral of y plus z ds, where our surface is 2x 3y plus 4z equals 12 in the first octave. All right, so how would we actually do this? Well, we have a choice here. We have a huge choice. We need to decide how we're going to define our function. We could solve for z, we could solve for x, or we could solve for y. Really doesn't matter here. I'm going to go ahead and solve for z because I think that's what most students generally do. So you can see if we solve for z here, z is equal to 12 minus 2x minus 3y over 4, or z is equal to 3 minus 1/2 x minus 3/4 y. So if that's our surface, let's see if we can figure out, now again, if you want to think about this in terms of what we had a second ago, that would be our function g of x and y. X 3/4 equals y. So this is going to be the double integral over the region. We'll see what the region here in a second is. Y plus z. Well, now we know that z is this. 3 minus 1/2 x minus 3/4 y. ds. Well, ds now is going to be the square root of 1 plus g sub x. The derivative of this with respect to x is negative 1/2. The derivative of that with respect to y is negative 3/4 dA. And again, we'll worry about what that region is in a second. But let's clean this up just a little bit. I'm going to bring it up over here. So we're still doing the double integral across our region. Inside our parentheses, what do we have? We have y minus 3/4 y, so that's 1/4 y minus 1/2 x plus 3. And what is all of this going to be? Well, that's going to be 1 plus 1/4 plus 9/16, 16/16, 4/16, and 9/16. That's 29/16, or the square root of 29 over 4 when you plug it back into there. So all that, lucky for this one, ends up being a constant, not necessarily a constant all the time, which we can actually pull out front. So that's the square root of 29/4. Region R, 1/4 y, 1/2 x, plus 3 dA. Now we still got a lot of stuff to figure out, because what do we mean by the region dA here? Well, if we take a look at what our surface is, and we've done this a couple of times, x, y, and z, where's our surface? So we get x is 1, 2, 3, 4, 5, 6. So x is out here. Z would be at 3, 1, 2, 3. Y is at 4, 1, 2, 3, 4. Okay, so that's what this shape looks like as it crosses into the first octet. So the idea here is we want to figure out what the region we're integrating across. What is this region area that we got to integrate across? Well, since we decided to solve for g or z as a function of x and y, this needs to be pushed down into the xy plane. So if we squeeze this down into the xy plane, 1, 2, 3, 4. That's our region. So in this case, if you think about it up here, it's this piece in the xy plane on the bottom that is our region that we're integrating across. Okay, so how are we going to integrate across from that? Doesn't matter which way we go. Remember, this is the equation if we let z be equal to 0. So this is 2x plus 3y is equal to 12. It doesn't matter if we do y or x first. So let's say we solve for y. So y is equal to negative 2/3 x plus 4. So in this region, let me go ahead and write our square root of 29 over 4. 1/4 y, 1/2 x plus 3. And we're going to do dy dx. Y runs from 0 to negative 2/3 x plus 4. Now once we integrate y out of this region, this collapses down to the x-axis, and x runs from 0 to 6. All right, so now it's a straightforward Calc 1-ish type integral. Integrate with respect to y, plug in your bounds. Integrate with respect to x, plug in your bounds, and that will give you the value if we integrated this function across that surface. So I'm going to leave that there because it should just be a bunch of arithmetic for you as of now. All right, now in the past we've also seen parametric surfaces. What if this was defined in terms of parametric? Well, not a lot changes from what we've had in the past. The integral over some surface, some f of x, y, and z ds, well, how does that translate into parametric? Well, we know for parametric functions, our surface, S, is defined some r of u in v, which is some x of u in v, y of u in v, and z of u in v. So all we got to do is translate that up here. So on the surface, and I'm going to leave this off for a second, On the surface, we know x is some u and v, so you put in whatever x is. Y is some function of u and v, put in whatever that is. And z is also some function of u and v. Put that into the function. So that converts our function over to the parametric. And we saw a second ago ds was the magnitude of r sub u cross r sub v dA, where that region you're integrating across is the domain for your u's and v's. All right, so let's take a look at another example. Let's see if we can get it set up. Let's say we wanted to find that, and I said find the value of the surface integral of, what did we do last time? We did y. Let's do x plus z, that's easy enough. ds, and again, let's say that our surface is r of u and v. Let's see, let's call this u 3 cosine v 3 sine v. And let's let u run from, I don't know, it doesn't really matter, to 4. And let's let v run from 0 to pi over 2. All right, real quick, let's take a look at what this surface is. Notice u is independent of v, and it's just in the x direction. So this thing is going to be some surface that just in the x direction goes from 0 to 4. So it's going to cover from there to there, from 0 to 4. What shape does this give us in the YZ plane? Because remember, this is x, this is y and z. Well, in the YZ plane, that's a circle of radius 3, but we're not doing the entire circle. We're only doing a quarter of it, right? We're only going a quarter of the way around. So let's see, if we put this 0 in, cosine of 0 is 1, and sine of 0 is 0. So at that point right there, that's here. So what we're going to get is, by the way, that's out here, 3. 3, 1, 2, 3. What we're going to get is we get kind of a half a circle here. So think about if you took a tube and you cut 1/4 of it out, and it has a length of 4. That's about what this shape is right here. All right, let's see if we can set up the surface integral for this. So what pieces do we need? Well, we need to go in here. And everywhere there's an x, we're going to put the function for x. Everywhere there's a y, we're going to put the function for y. Everywhere there's a z, we put the function for z. So let's get our scribble out of the way. Wasn't that good anyway. So our surface integral is going to become, x was just u, z was 3 sine v. Okay, so that's this piece. That's where we plugged it in. Now we got a bunch of side work to do. We need to find r sub u, r sub v, then do the magnitude of that cross product. So I'm going to go back up here where we started, so I'm going to set it all up over there. So by looking at this, r sub u will be 1, 0, 0. R sub v will be 0, negative 3 sine v, and 3 cosine v. So r sub u cross r sub v. So get that piece out of here now. I, j, k, 1, 0, 0, 0, negative 3 sine v, 3 cosine v. So in the I direction, we get 0 and 0, so no i's. Minus, in the j direction, I get 3 cosine v minus nothing. J, and in the k direction, I get minus 3 sine v k. All right, we have to remember our bounds here for a second. So this ends up being 0, negative 3 cosine v, and negative 3 sine v. For our formula, we know we need the magnitude of that, magnitude of r sub u cross r sub v. That's the square root 0 plus 9 cosine squared v plus 9 sine squared v. Hopefully it's pretty obvious here. You could factor out the 9, you get sine squared, cosine squared, square root of 9, or 3. Okay, so this is going to be 3 dA. Now remember, for our domain, I just erased it a second ago, we have a u and a v. We said u went from 0 to 4, and v goes from 0 to wherever pi over 2 is. By the way, it's too much for pi over 2. I just put some hash marks on there. Okay, so we end up with this rectangle. So we're going to integrate u plus 3 sine v. There's our constant comes out front. Doesn't matter if you do du dv or dv du, so I'm going to do du dv. We can see u goes from 0 to 4, v goes from 0 to pi over 2. So again, our bounds are very, very easy to figure out when we're doing this in parametric form. All right, again, basically a calc 1 integral. See if you can finish that up. Should be pretty easy from now on. So surface integrals, we're adding up the value of a function across every point on a surface.